This video is on Poisson distribution, and we say that the random variable x has a Poisson distribution if it has the following probability density function of PDF of f of x equal to lambda to the x times e to the negative lambda dividing by x factorial, and where x takes on the values of 0, 1, 2, 3, 4, so on, and lambda is a positive number. And in this video I want to show that the expected value of x is lambda and the variance of x is also lambda. And so the first part here I want to show that the expected value of x is this quantity lambda right here. So the expected value of x is the sum from 0 to infinity with the expression x times f of x. And then I'm going to write out the first term when x is 0, and then we get 0 times f of 0, and then plus the sum starting with x equal to 1. And then we can see that right here, this is 0. And therefore the expected value of x is just the sum with x starting at 1, and then with the expression x times f of x. F of x is lambda to the x times e to the negative lambda dividing by x factorial. X factorial is x times x minus 1 factorial. The summation here is with respect to x, and therefore we can move the quantity e to the negative lambda to the front. And then this x and this x, they will cancel each other out. And then what's left is just lambda to the x dividing by x minus 1 factorial. And now let c be x minus 1. Recall that from calculus we have the Taylor series for e to the x is the infinite sum with c starting from 0, and then with the expression x to the c dividing by c factorial. So this is the Taylor series expansion for e to the x. And so now rewriting x in terms of c is equal to x minus 1, and so x will be c plus 1. So in the place of x, we have c plus 1. This is x minus 1, and so which is c. And then when x is 1, c is 0. Lambda to the c plus 1 is the same as lambda to the c times lambda to the first. And then we can move lambda to the first to the front and place it in front of the summation sign here. E to the x is the infinite sum of x to the c dividing by c factorial. And so the infinite sum of lambda to the c dividing by c factorial, this right here, this is e to the lambda. This is e to the x, and so this is e to the lambda. And therefore the expected value will be lambda to the first times e to the minus lambda, and then this sum right here is e to the lambda. E to the minus lambda times e to the lambda is 1, and so we get lambda. And therefore the expected value of the random variable x that has a Poisson distribution is lambda. And now I'm going to show that the variance of the random variable x is also lambda. And to show that the variance of x is equal to lambda, first let's find the expected value of the expression x times x minus 1, which is the infinite sum of x times x minus 1 times f of x. And then here I'm going to write out the first two terms. When x is 0, we get 0 times negative 1 times f of 0. And then plus, when x is 1, we get 1 times 0 times f of 1. And then plus the infinite sum starting with x equal to 2. And then we can see that this part here is 0 and this is 0. So we get the infinite sum starting at 2 of x times x minus 1. And f of x is lambda to the x times e to the negative lambda dividing by x factorial. And then x factorial is x times x minus 1 times x minus 2 factorial. And then we can see here that the this x and this x, they cancel each other out, and then the x minus 1 here, they will also cancel each other out. And then we can move the e to the negative lambda and place it in front of the summation sign right here. And now let c be x minus 2. And then in the place of x, we have c plus 2. C is equal to x minus 2, and so x is going to be c plus 2. X minus 2 is c. When x is 2, c is 0. Lambda to the c plus 2 is the same as lambda to the c times lambda to the second, and then we can move the quantity lambda to the second and place it in front of the summation sign right here. And just like a few moments ago, this quantity right here, this infinite sum, this is e to the lambda from the Taylor series expansion. And so we end up with e to the negative lambda times e squared, lambda squared times e to the lambda. And then of course e to the negative lambda times e to the lambda is 1. So we end up with lambda squared. And so, so far we have seen that the expected value of x is lambda, and then the expected value of the expression x times x minus 1 is lambda squared. X times x minus 1 is the same as x squared minus x, and so expected value of x squared minus x is the same as expected value of x squared minus expected value of x. And therefore from here we can see that expected value of x squared is equal to expected value of x times x minus 1 plus expected value of x. This is lambda squared, and this is lambda. The variance of x is the expected value of x squared minus expected value of x squared. So we get lambda squared plus lambda, and then minus lambda squared, and so we get lambda. And so in summary for the random variable x, that with the Poisson distribution, the expected value of x is lambda, and the variance of x is also lambda. And now let's work in an example. And so suppose we have customers enter a store ABC on the average of 5 customers per hour. And let's make the assumption here that we have a Poisson process. And so we want to know what is the probability that 7 or more customers entering store ABC in a 2-hour period. And so let x be denote the number of customers entering store ABC in a 2-hour period. And so on average, we have 5 customers entering the store per hour. So for a 2-hour period, we expect 10 customers to enter the store ABC, and therefore the expected value of x, which is lambda, is equal to 10. we want to find the probability that x is greater than or equal to 7, which can be rewritten as 1 minus the probability that x is less than or equal to 6. Probability of x less than or equal to 6 is the sum from 0 to 6. Lambda is 10, so we get 10 to the x times e to the minus 10 dividing by x factorial. And then we can move the e to the negative 10 and place it in front of the summation sign right here. And then evaluate this sum right here, which is this. And it's going to be 1.13014142. And then 1 minus 0.13014 is going to be 0.8698. And therefore the probability that 7 or more customers entering store ABC in a 2-hour period is going to be 0.8698. And that's the end of the video.